So we are going to talk about IoT deployments from a mobile core network perspective, then discuss why and how IoT deployments and applications could pose an overload threat to core network elements and applications, and then discuss a bit about our work, the development of an enhanced overload control function reusing some augmented intelligence methods to overcome these overload threats. To talk a bit about myself, my name is Mitropoulos and I'm a member of Nokia team several years now. I started as a member of the technical staff for next generation voice over IP application servers and media gateway control functions. And for the last 5 years, I'm a member of the architecture team working for 4G and now 5G core network elements. All right, so this is a projection of the market share of some of the key mobile network applications, one of them being the Internet of Things, that have or may have against different generations of the mobile networks, starting from 3G to 4G and now 5G. Internet of Things were first introduced in 3GPP specification release 12, that is a few years back. And during that time, it was expected to be first widely used in 4G networks. Finally, that didn't happen, at least not as much as originally expected. However, now, with 5G networks being deployed, IoT is considered as one of the cornerstone technologies for 5G, as it is expected to be used in diverse vertical services such as healthcare, agriculture, manufacturing, public facilities, and connected cars in small-scale private 5G networks to large-scale commercial 5G mobile networks. Now, this is really the reason why it is expected that an end user will be now owning around 25 end devices compared to 1 to 3 devices that an average user owns today. So, operators and service providers do see a business potential on IoT. And now that the 5G has been deployed, are willing to invest on it. But investment usually starts on the spectrum and radio access network resources needed to support the new service deployment. And then operators expect to reuse as much as possible the core network resources. This means that when IoT is being deployed in massive manner, then from a core network application perspective, there is need to accommodate significantly higher number of registered UEs, each UE being an IoT device. But then, because of larger number of registered users, even if having same nominal traffic, still the core network application will most probably need, at some point, handle more severe burst of traffic during some network abnormality, or even because of some mishandling from the network administrator himself, that, for example, may attempt to do at once some firmware upgrade or massive data collection from all deployed IoT devices. So, more registering devices means higher possibility and risk of overload condition. And this will definitely pose a challenge to the existing overload control functions that is applied in core network applications. And let's see why. Let's assume that this figure represents some internal KPI in one of core network compute resources. For example, this could be the CPU usage against time. And let's assume that this red line is a KPI and then this white line here is that KPI overload threshold. In case of CPU, that could be selected to be on the 95% of the available CPU resource. Now, this white line here is the same KPI when system is in idle state, which means when there is zero incoming traffic. Now, anything above this line here, which means anything inside this gray box here, is considered to cause some sort of overload condition. Now, in all overload control functions, the objective is to avoid entering this area here, which means to avoid entering overload condition, no matter the size or fluctuations of the incoming traffic. And this is achieved by either silently dropping this excessive signaling or rejecting all of this existing signaling and requests by adding a retry after information element in the reject response. This retry after is actually an instruction to originating side to retry the same request after this retry after timer expires. Now, the problem with all these traditional overload control functions is that these methods in practice are not really proactive, but react after the overload event has occurred, which means, in this case, after having gone through this point here. And this means that in most of the cases, the application has already ended overload when overload is actually detected. And when that happens, the application will most probably stop acting in linear manner and the system performance will degrade. Now, even if suggest placing the overload control threshold to some lower level, to what we have named in this graph as safety net, then this means that we will need to give up some of the capacity that internal resources may offer. So this is definitely not the best option to select. Now, as said, optimum performance means keeping always the internal KPI right below this threshold, no matter the incoming traffic. So to achieve this, we need to add some intelligence to the existing overload function in a way so that the function may somehow foresee a network event, for example, a burst of traffic, before that event happens. And that will give to the core network application an edge in the handling of that event, of that, for example, excessive traffic. So let's have a look on how this augmented overload control function could look like. Okay, now this is a high-level overview of the enhanced overload control function that we developed to perform exactly that. Now it involves three functions: sampling, assessment, and then verdict. Now, the method monitors the internal KPIs, some key internal KPIs against the incoming traffic, do some sampling on them, and then feed all these samples to the risk assessment function here. Now, this is where the risk to enter overload state is assessed based on some rules. And then verdict is applied, and which is where decision making takes place, which means deciding on the appropriate action based on the assessed risk. Now, the assessment means doing some sort of prediction, which means try or attempt to foresee a network event that could trigger overload before it actually happens. So an important step for the success of all of this is applying the right prediction function. There are several analytic functions available that can be used for such a purpose. Some well-known and used are the regression analysis models, with quite many variations to use. For example, there's the linear regression model, the polynomial regression model, the random effects model, and others. In all of these models, it is actually attempted determining the relationship between some cause and some effect. The independent variable is the cause, and the dependent variable is the effect. So for our example, in our application, the independent variable could be the incoming transactions, the number of the incoming transactions, whereas the dependent variables are the internal KPIs. Now, take for example the simple linear regression function. The simple linear regression function attempts approximating the relationship between the dependent variable and the independent variable by a straight line. Whereas, for example, in a polynomial regression, the attempt is approximating that same relationship, but this time by the nth degree polynomial function. Just a note here, in any of these prediction methods, we are not really trying to represent this relationship by a deterministic function alone. But instead, we do want to have some statistic factor involved, because we do want to have some randomness involved anyway, like an educated guess, given that anyway there is some randomness involved with incoming traffic, especially during periods of excessive traffic caused by some sort of network abnormality. So let's try to visualize how regression analysis is used with an example. by looking again the figure of internal KPI change over time. Assuming that we have picked a linear regression analysis function to associate the internal KPI against the incoming traffic, then as more samples are fed to the regression function, then the model updates the prediction by new linear representation. And from that, we have the updated prediction of the internal KPI, which means moving from this line here to this one here, and eventually to this one here. As it can be seen from the graph, even with a small number of samples, the function is able to follow the KPI's actual change over time. But to be fair, for this case, this is happening because the KPI fluctuations are quite smooth and slow in change. So a linear regression is quite adequate for this case alone. Unfortunately, in real networks, things don't happen this way or don't happen always this way. The fluctuation is often quicker in change due to the burst nature of incoming traffic, as it may happen when several IoT user data exchange is involved, or when there is some abnormality in the network. For example, when there is some gateway failure. So we talk about the assessment risk function. So one thing is selecting the right analysis function for your application, but still after selecting the analysis function, you still need to take care of all the attributes involved with its analysis function. And trust me, all of these attributes do bring a lot of complexity during the implementation. Even when applying the simple linear regression method, there is still complexity involved that needs to be handled. To name a few, someone needs to properly pick the number of samples to fit the function and even select the sampling rate. Let's have a look on some of the preliminary tests that we did while trying to get a better understanding of how these different attributes affect the prediction. Now, on the graph displayed on the screen, there is a representation of the internal KPI values over time, where the green dotted line is the actual KPI, whereas the yellow dotted line is the predicted KPI. As it can be seen from the graph, in general, the prediction does resemble the actual KPI values, except from some areas, as highlighted here and here. Now, this deviation of the prediction from the actual KPI isn't necessarily bad. Remember, we are not trying to 100% match the KPI change, as we do want to keep some randomness in our prediction. So, selecting the right assessment function and doing the fine-tuning of the associated attributes is an important factor for the success of this case, but do require a lot of work and definitely it takes a lot of time during the implementation of the function. Now, equally important, however, to the assessment, to the risk assessment function is the proper strategy applied under the verdict function. So let's talk about verdict. Now, verdict is first decide to take some action based on the risk assessment, and then decide on the action itself, which is the policy. Now, the policy applied is important. It is even more important than the method selected to perform the prediction. The reason for this is that in telecom network, the transactions aren't equal in terms of significance, both to the network and to the end user, in terms of impact for transaction processing need, and in terms of severity in case of transaction failure or rejection. So there is difference in network impact, for example, if the network fails some handover or mobility event, than the impact, example, when the network fails some user attempt to run a service. Think, for example, the New Year's Eve, when only seconds after 12 o'clock, everyone is trying to make a phone call or text a friend or loved one, or even upload some picture to some social media application. The network will most definitely quickly become overloaded and then start rejecting some of the incoming service requests. Now, most of the user, when this happens, will insist on trying. Eventually, the user will become even more frustrated and they keep on trying and trying for the same service request, as they don't get the requested service fulfilled, which means that the service rejection, which were a mean to protect the network from the overload condition, finally caused even bigger bursts on the incoming traffic with even more severe consequences. So all of this means that the strategy applied needs to be carefully picked. And trust me, during the implementation of our function, this was one of the items that we really struggled to develop. Now, let's proceed to the next slide. Okay, so let's have a look on the testing performed and the results of our enhancement function. Now, the figure here is an abstract representation of the involved packet core architecture, which is the 4G network architecture. Now, this is us. This is the MME, or mobility management entity, that is responsible for the authentication, authorization, session, and mobility management and control for all 4G subscribers. This is where the application and the overload control enhancement run. Rest of the network involves the end users, the eNode Bs. This is the radio access network, the S&P gateways that act as user plane gateway to the external network that run the applications, and then the HSS, the home subscriber server that carry the subscriber profile. Now, so for our testing, we used Nokia NLG product as traffic simulator. The traffic applied in some of the tests resembled real customer network incidents. Now, in some other of our tests, we went further than just that. So we did several tests with multiplied traffic that extended several times above the nominal traffic rate. In our case, for the large configuration of our product, nominal transaction rate is approximately 75,000 transactions per second. Now, we also ran some cases where during an overload condition, the network suffered some sudden loss of one of our application service instances, or some gateway failures causing even more abnormality for the incoming traffic. All right, let's move on to the results. Now, to evaluate the enhancement function, we use two key performance indicators. A, the number of transaction failures, and that failure could be because of the transaction got rejected or because the incoming transaction request got timeout. And B, the amount of time consumed until full system recovery. And full system recovery means that in our case, that the transaction success rate returns to 99.999%. Okay, so let's have a look on the results with and without the enhancement. Now, the left column graph depicts the results of our testing where the application didn't carry the enhancement, whereas the right column graph depicts the results of our testing with the enhancement applied. Now, on the graph, the focus is on the red lines, and these red lines depict the number of failed transactions over time. As said, the failure could be because of transaction timeout or because of an error code sent back in response message. Now, comparing these two graphs, it can be seen, A, that there is less number of failed transactions per second. Actually, with the enhancement, we have achieved 3 times improvement compared to when there is no enhancement involved. And B, the application has managed to recover in much quicker when the enhancement is applied. Going to the next set of results, these graphs here depict the aggregated number of failed transactions over time, where again we can see here where this is the result when the enhancement is applied against the graph here with this is the application running without the enhancement, where we can see here and here that actually there is a significant improvement in the application performance when the enhancement is applied. So the benefit is having more than 1 million less failures when the enhancement is involved. Similar improvements have been found with all that is performed. So from this, we consider that the introduced enhancement is really successful, adding robustness to the performance of our application. So to summarize, the diversity of cellular IoT applications may introduce randomness in traffic that could pose overload threat to core network applications during traffic bursts. Now, current work attempts to reuse some of the augmented intelligent techniques so that imminent overload conditions may be identified and then take preventive actions. Now, to overcome these threats, we developed an enhanced overload control function that proved to offer clear benefit under more severe network conditions. Now, as the next step, there is one item of interest. Further enhance and modify the function that we have already developed by this time, use it for a different purpose. Use it to identify communication patterns, either large scale, communicator patterns affecting the entire application, or communication patterns per user. That is traffic patterns, and then use that for example, to optimize compute resource planning that is most useful, especially in 5G networks. And that's it from my side. Thank you very much.
Hello, George.
Hello.
Hi, so thank you for the interesting topic. And we have two questions from you, from the audience. So can you clarify on the platform, hardware, or system used, or maybe this is irrelevant? Or do you see applications of this for other technology sectors, maybe?
Okay, to answer the first question, if it is really relevant or platform specific, the answer is irrelevant. Actually, we built it this way. We wanted to build it this way so that it is relevant, so it can be, if possible, directly reused on other products for Nokia. Regarding the second question, if there is other applications or technology sectors that could benefit from this, the answer is yes. I provided an example in the last slide that the direct enhancement of the existing function is that to be reused to identify communication patterns that can be used for telecom sector, of course, but anyone looking to somehow create something that uses pattern recognition could benefit from this function. So yes, there is another technology sector that could benefit from it.
Okay, so, and our next question is, are there real life examples that you may have from operators that Nokia has, and in which you have seen excessive deployments of IoT applications and relative challenges? Or, okay, maybe this is something that will mainly boom with 5G, so.
Right, so we expect it to be used mainly starting from 4G, right? But actually the operators never really used it. And for 5G now, yes, I think it is one of the cornerstone of 5G, really. It will be used in several vertical services. So it will be in everyday's life. So I expect that there will be a significant market share for IoT in 5G, and I expect that operators will invest on it. Okay.
Okay, and our last question is about how telecom networks are different from other network functions in terms of high availability and robustness. Do you have any examples and maybe hints?
Well, I'm not sure if there is a difference, really. I mean, all wanting to provide a particular service to any user want to be highly available and be robust enough, which means 99.999% of the time needs to be available. No one wants to have an outage in the service providing. So I think there is no difference from this aspect.
Yes, I agree. So that's all we have and the questions. Thank you.